Okay, the next presentation is by Dr. Delia Milliron from the University of Texas at Austin. She is a professor in the McKetta Department of Chemical Engineering at the Cockrell School of Engineering at the University of Texas at Austin. She has advanced technology that could revolutionize how windows are used in modern architecture by developing a new material that, when applied to windows, can dramatically control the amount of infrared light that passes through. The smart window technology allows visual interaction with the outdoors without allowing either too little or too much heat from the sun to enter the room. This could result in significantly reduced energy consumption in buildings of the future, and as a member of the oil industry, I'm sorry to hear all this, but maybe you'll put us out of business. So, Dr. Milliron.
And now for something different. Great. So in my lab at University of Texas, we're focused on using the tools of chemistry to craft the composition and morphology of nanostructured materials to specifically tune and customize their electronic and their optical properties for different applications. In today's talk, I'm going to focus particularly on our work over the last few years developing metal oxide nanocrystals that have these unusual optical properties in the infrared that were just alluded to. So I'm showing one of these nanocrystals on my opening slide here. It's the rounded square is an electron micrograph of one of our nanocrystals that I'll obviously show you much more of. And what you're seeing is data also from the electron microscope highlighting a resonant interaction of this nanocrystal with infrared light that gives rise to very intense hotspots of incredibly high electric field around the corners of this nanocrystal. And that concentration of diffuse energy from infrared light into these nanoscale volumes is one of the very special optical properties of the materials that I'll be discussing. Normally, this kind of energy concentration requires a metallic material, whereas metal oxides are typically insulating. So one of the keys that I'll go into in my talk to creating this kind of so-called plasmonic resonant phenomenon is to add impurities to the metal oxides that render them conductive, and that gives rise to the sort of optical properties that you see here. So here's a gallery first of electron micrographs of metal oxide nanocrystals, all of which have been doped with these impurities or have some impurities introduced or off stoichiometry change the composition of the material to give rise to this kind of conductive behavior. And these are things we've developed in my lab and others in the community have developed over the last few years, just sort of highlighting the diversity of compositions and shapes and sizes of these nanoscale materials that we can craft using the tools of inorganic synthetic chemistry. So you see, for example, some very earth-abundant compositions that have the potential for large-scale applications like our window coatings, like aluminum doped into zinc oxide, for example, and some more exotic things like cerium doped into indium oxide, which has very special properties electronically, and so it's interesting in that regard. All of these materials, what you're seeing in these images is the inorganic metal oxide core of the nanocrystal, but they're actually all hybrid materials. So the surfaces of those nanocrystals, although you can't visualize it in the electron microscope, are capped by a molecular layer of organic surfactants or ligands that allow them to stay dispersed or suspended in the solvent while we grow them in our chemical flasks in the lab, and also allow them to be dispersed into solutions or dispersions, as you see in the photograph, that enables us to post-process them very easily to make large-scale coatings on glass or integrate them with other materials, and I'll show you some examples of that. So why is it important that we can make many different compositions of these materials? For us, one of the key benefits of that is that each composition has a unique optical signature with respect to its interaction, its resonant interaction with infrared light, that gives rise to a very strong absorption of infrared light of a specific frequency. So I'm showing here the absorption spectra for a variety of different doped metal oxide materials, and you can appreciate at a glance that they cover a wide range of energies of infrared light. Some of them are very broad, some of them are quite narrow, some of them are even multimodal or have two peaks underneath the absorption envelope. So by selecting the material, we can really choose which sort of infrared light it's going to interact with and what the nature of that interaction will be. And that's true not only by selecting the material itself, for example, aluminum doped into zinc oxide, but because we can control the amount of that dopant or impurity added, we can further fine-tune the optical response of the material. So here, for example, the two red spectra on the right are both aluminum doped into zinc oxide, and we've just varied how much aluminum we use in the synthesis, and you see this significant shift to the peak. And the same is true of any of those compositions that I've showed you. So we really have this incredible library of materials where we can tune the spectral response in the infrared spectral region just using the simple tools of synthetic chemistry. So what really is the nature of this absorption or this resonance that I keep referring to? How is it that these materials interact with light? So this phenomenon of metallic or conductive particles interacting with light is known as localized surface plasmon resonance. And it's been very well studied over the years, mostly in classical metals like gold and silver. So the schematic on the left shows you how the electrons, which are very abundant in these metallic materials, can be polarized in an alternating fashion by the incoming oscillating electric field associated with the light that's arriving at the particle. So you see this oscillation, this resonant oscillation of electrons that gives rise to the characteristic absorption peak of the material. Now, as I mentioned, metal oxides are not typically conductive. They're usually insulators. So in order to have this kind of plasmonic resonance, we need to introduce a significant population of mobile electrons, and that's where the dopants really come into play. So for example, in our prototype material, tin-doped indium oxide, otherwise known as ITO, some of the indium atoms, or ions, are substituted by tin. And every tin atom brings along with it an extra electron. So if we dope an appreciable amount of tin into the material, we can establish a high electron concentration and give rise to plasmonic resonance, just as in classical metals. That also makes the materials conductive. And because we can control the amount of dopant, we can therefore tune the electron concentration and hence the resonant frequency, the type of light that these materials interact with. Now, it's always going to be much lower than in a metal like gold or silver, so that gives rise to these electron concentrations that move the resonance from the visible, where gold or silver would interact with light, into this IR spectral region. So far I've been talking mostly about tuning the optical spectrum of the material, what kinds of light it absorbs. But there's another type of optical properties that has to do with the concentration of the energy from light into small volumes that I alluded to on my title slide. So I want to illustrate that for you a little bit further. So shown schematically here is the wavelength of infrared light, which is quite long wavelength light compared to visible, as the orange wave there. And in the middle, in the blue square, is schematically shown actually one of our larger nanocrystals drawn to scale so that you can appreciate how much smaller these nanocrystals are than the wavelength of light. So typically, with lenses and classical optics, the spatial region that you can concentrate light into is related to its wavelength. So it's approximately shown by this gray circle. And what we're able to do by virtue of this plasmon resonance is to concentrate that light down to the size of that nanocrystal, and in fact, to concentrate it even further. So as you can see illustrated by this energy loss map taken in the electron microscope by my collaborator Emily Ringe and her team, these hot spots, these intense red spots around the corners of the nanocrystal are showing you the very small nanoscale volume that we've taken this very long wavelength light and concentrated it into. So that is not the far field, but the near field optical property of the material, and it has other potential applications that I'll come back to later in my talk. But first, let me tell you what the far field optical properties, the tuning of the spectra, can be used for, and that has to do with the smart windows application that you heard mentioned. And actually, the problem of smart windows is what drew me to work on metal oxide plasmonic materials in the first place. I was able to interact with colleagues who had collaborated with the glass industry and with architects over decades, and they helped clarify for me where the challenges lay in this field. And what I learned is that technologies exist and in fact are now beginning to appear in buildings, you may have seen some of them around, that can modulate or dynamically tune the tint on the window. So sunlight is composed in roughly equal parts of energy of near-infrared light, which we can't see but contributes to heating, visible light, which obviously we do see, and a small fraction of UV light. So these windows that are now out on the market are electrochromic in the sense that as a voltage is applied and the window accumulates charge, it can be on demand switched between a clear state and a tinted state. However, they mostly block the infrared light, so they're not very good at allowing for solar heat gain in the winter when it's cold, as on mornings like today. So our vision when we got into this field was to create a more universal functionality for smart windows where we could dynamically control both the infrared light and the visible light selectively so that we could have or reject solar heat gain on demand and also control the sunlight or the daylighting potential of the windows and the glare that can make interior spaces uncomfortable. So the piece of this puzzle that was missing when we got into the field was really the top part of this, some way to selectively modulate the transmission of infrared light while the coating on the glass remains transparent to visible light. And that's where our nanocrystals come into play because they have this very tunable infrared absorption while being transparent to visible light. But chemical tunability is not enough for this problem. We needed to be able to post-synthetically, on demand, by applying a voltage, tune the infrared transmission. And that's what we were able to do when we made a film or a coating of our nanocrystals on glass and applied a variable small amount of voltage, just a couple of volts. And what happens in this case is that the electrons, which are present from the dopants, can be shuttled in and out of the nanocrystals as a variable voltage is applied, thereby modulating very strongly this infrared absorption due to plasmon resonance. And you're seeing the range of tunability here, all the while the material remains transparent, so nothing is apparent to your eye. And later, we were able to embed these nanocrystals in a second material to make a composite coating on the glass that could accomplish what we had initially set out to do, independent control over visible and infrared light. So I'm showing you here the spectrum of this glass as originally coated. It's quite transparent, as you can appreciate in the photograph. And as we begin to add electrons by applying a voltage, initially they collect in the nanocrystals, instigating this plasmonic resonance and therefore infrared absorption. So we're now blocking a large portion of the solar heat gain. As we continue to apply a voltage and add charge to the film, now it triggers a second electrochromic response in this matrix material, which is niobium oxide, and that gives a visible tint to the glass, as you can see in the photograph. So selectively, depending on the voltage we applied, we have a window that can be transparent to both IR and visible light, allowing maximal solar heat gain for cold days when it may not be so bright out. We can selectively block the heat gain by blocking IR and maintaining daylighting. And then if we need to further reduce heat gain or control glare, we can also tint the glass. So these are now under development to be embedded into dual pane glass windows, the typical modern windows, where our electrochromic glass will replace probably the outer pane of glass in a normal window, and there will be embedded controls in the window frame that allow building control system or a switch on the wall to modulate the heat gain and the light. Okay, so this takes advantage of the tunable and dynamically modulatable infrared absorption. But what about the near-field optical properties? What might these be good for? So this work is at a much earlier stage, so I'm just going to provide you a little bit of a vision for where we think we could apply this amazing ability to concentrate light into nanoscale volumes. In particular, remember that this is infrared light. And infrared light, besides resonating with our nanocrystals, is the natural resonance frequency for molecular vibrational modes. So this is used for chemical identification, and it can be a key component of sensors. So for example, the molecules I'm showing here for detection, these are common indoor air pollutants that we might want to sense at very small levels before they can impact human health in a substantial way. Molecular vibrations are also important in manipulating catalytic outcomes. So if we can channel energy into specific vibrational modes of reactance or perhaps transition states, we envision that we could modify the distribution of products from typical catalytic reactions and perhaps improve efficiency in that way. So the first step to accomplishing any of these goals would be to couple the energy from one of these plasmonic resonances into other oscillators nearby. And before studying the coupling to vibrational modes, which is a bit challenging, we can get a hint about the coupling potential by looking at pairs or even small groups of these nanocrystals together, again, in the electron microscope. And what we see here is that when we have two nanocrystals close together, as shown on the left, that instead of having their individual plasmonic modes, that they couple together, and we see plasmonic modes of the overall coupled system. So there's one longitudinal mode with hotspots on either end and one lateral mode. Similarly, for this square arrangement of 4 nanocrystals, you can see that we get overall modes that are coupled within the system that create exceptionally high electric fields in between the nanocrystals, in those spaces where they're adjacent to one another. And we expect, therefore, that we can have very high concentration of field between nanocrystals in simple assemblies, like the one I'm showing you an image of here. And in front is a simulation of the expected enhancement of the electromagnetic near field from the light up to many orders of magnitude above what it would be in the diffuse limit, where the IR light is simply shining on our nanocrystals. So it's particularly useful that the highest concentration of electric field is between the nanocrystals, because remember that this is not empty space. We actually have organic molecules present at the surface of the nanocrystals. So those organic ligands that coat each nanocrystal are still there in these assemblies, and even though they're very thin compared to the size of nanocrystals, they populate that space just where the electric field is highest. And that gives us the opportunity to couple very strongly that light into those small volumes between the nanocrystals and therefore into the bonds of those molecules. And in fact, when we look at the spectrum, which is shown here in red, of such an assembly, we see evidence of that strong coupling between the nanocrystal's plasmonic resonance and these specific vibrational modes of the molecules. So this little wiggle that you see in the spectrum that's shown in the inset in the red line has a characteristic derivative-like shape that's typical of strong coupling. So it's the first evidence that we can harness this very diffuse light source, diffuse energy source of low energy IR light, and channel it specifically into these molecular vibrations. So looking forward then, we're very excited to begin to address these questions of whether plasmonic resonance can, in this way, interact with specific modes of reactance and transition states to modify catalytic outcomes and product distributions. We already know, I should say, from the spectrum I just showed you, that we can enhance detection selectivity or detection sensitivity. And so we're also looking into opportunities to create detector systems on the basis of that principle. But we're also going back to the chemistry lab and our ability to tune these materials in increasingly sophisticated ways to further craft their near and far field optical response. So in particular, the image I'm showing on the right here is an illustration of one of our most recent advances in the lab, where we've learned to control the spatial distribution of the dopant. So not just how much of the indium is replaced by tin, but here we specifically place the dopant near the surface of the nanocrystal. And we can place it in the core if we want, and we can place it in both, or we can modify the distribution of dopants, which changes the electrostatic landscape across which these electrons are moving when under the influence of the electric field of light, and thereby changes the potential for the near field enhancement and coupling properties. And ultimately, our vision is to incorporate both of the things I've showed you, the potential for coupling our plasmonic resonance to other systems to do useful work, and the potential to dynamically modulate them as we do in our smart windows, so that we could build catalytic systems, for example, that can be dynamically tuned to change product outcomes. We can build detectors that can be dynamically tuned to detect different types of molecules over time, depending on the application environment. So that's some of the future directions that I hope to be able to share with you at a future date. But for now, let me reiterate my thanks to my incredible collaborator, Emily Ringe, and her team who have been at Rice University, and to the team of postdocs and students who have worked with me. I've listed the names of those who've recently contributed specifically in this Plasmon area here at the lower part. And again, thank you very much for this recognition and for the chance to share some of our work here today.